Hi, welcome to my talk. My name is Anand Kamath, and I am a PhD student at the HgSe group at the University of Chicago. Today, I'm going to talk to you about my work on slowing the non-radiative relaxation in mid-infrared quantum dots and its application to make sensitive mid-infrared detectors. Let me first start by motivating my work. The goal of my work is to make thermal cameras affordable and efficient. Over 35,000 Americans die due to road accidents each year, and 95% of these accidents are due to human error. Self-driving cars give a solution to this pressing problem, but they are not yet safe to completely replace human drivers. The most hazardous conditions are during the night and during rainy and foggy days, where the cameras of the vehicle perform poorly. Thermal cameras using the mid-infrared wavelength are necessary for making self-driving cars safe. This is because the long wavelength can pass through fog and rain, and these cameras can even work in the night. But the reason that these cameras are not yet being used is that they are insanely expensive. A megapixel thermal camera can easily cost more than $50,000. To solve this problem, our lab at the University of Chicago is developing thermal cameras using quantum dots. The main benefit of these quantum dots is that they are very cheap to fabricate. The current material to make thermal cameras are mercury cadmium telluride alloys, which are made by molecular beam epitaxy, which makes them very expensive. In comparison, quantum dots can be made by a very simple chemical synthesis, and this can bring down the cost to around $1,000 and revolutionize this technology. Quantum dot infrared cameras currently are good but not great. And the main challenge faced by these quantum dots is that they need to be cooled to cryogenic temperatures to operate. Here we have the detectivity versus temperature for mercury telluride quantum dots, which are the most common quantum dots used for thermal detection. On the y-axis, we have the detectivity D star, which is a measure of the signal to noise. And this tells about the performance of the detector. And here we have the temperature on the x-axis. We can see that the detectivity decreases exponentially as the temperature is increased. And this is because the noise increases due to thermal recombination. The ideal detectivity goal is this horizontal line near 10 to the 11, and this is called background limited infrared detection, or BLIP. We can achieve background limited detection around 120 Kelvin, but this is not an option for cameras because this makes them bulky and expensive. So the holy grail is to achieve background limited detection near room temperature, and this is denoted by this star over here. And we are currently 2 orders of magnitude below this level. So we need some method to reduce the noise without cooling the detectors. And we can do this by slowing the non-radiative relaxation in these quantum dots. The detectivity goes as a square root of the non-radiative lifetime, which is proportional to the PL quantum yield. Right now, the quantum dots suffer from a fast non-radiative process, which is of the order of a few hundred picoseconds, and the quantum yield around 10 to the minus 4. So in order to make efficient mid-infrared detectors having background limited performance near room temperature, it is necessary to design quantum dots which are bright and have a slow non-radiative decay. Before we can slow the non-radiative relaxation, it is necessary to first find the mechanism of relaxation. On this slide, I'm going to discuss 3 common mechanisms of non-radiative decay. Here on the left, we have a cartoon of what a quantum dot looks like. A quantum dot is a semiconducting nanoparticle with organic ligands on the surface, which are used to stabilize the quantum dot. Here we have an actual picture of a quantum dot seen under an electron microscope. Over here, I have a cartoon of a quantum dot with 2 electronic energy levels and ligands on the surface. When the quantum dot absorbs a photon, an electron and a hole are created. The first mechanism is called surface trapping, in which there are defect states on the surface of the quantum dot. The electron or the hole relax to these defect states and get trapped, after which they relax back to the ground state non-radiatively. Surface trapping is similar to the Shockley-Reed-Hall recombination, which is the dominant mechanism for silicon and other wide-gap semiconductors. The second non-radiative mechanism is unique to quantum dots in the mid-infrared. In this mechanism, the quantum dot energy relaxes radiatively and releases its energy to absorption of ligands on the surface. And this coupling is by a Foster resonance energy transfer. And this model is called the FRET model to ligands. The third mechanism is called multiphonon relaxation. The phonons are atomic vibrations of the atoms in the lattice of the nanoparticle. In this model, the electron transfers its energy to form a high order phonon state. Over here, it is important to emphasize that among these three mechanisms, the first two can be overcome by engineering the surface of the quantum dot, either by removing the defect states on the surface or by changing the surface ligands. But since phonon relaxation is intrinsic to the material, there is nothing that can be done to overcome this. And this would be a dead end to the performance of quantum dot detectors. So to find the mechanism of relaxation, I have designed a strategy to grow a thick shell around the nanoparticle. By growing this shell, we are separating the active core material from the surface of the nanoparticle. Since the three models obeyed fundamentally different physics, the growth of this shell has different effects on the non-radiative rate of these three mechanisms. Over here, I have the simulation for the PL quantum yield as a function of the shell thickness. The PL quantum yield is a direct proxy for the non-radiative lifetime, and it is a useful quantity because it is easy to measure experimentally. The first mechanism, which is surface trapping, involves a quantum mechanical coupling of the electronic wave function with defect states on the surface. So as we grow a shell, we should expect the non-radiative decay to obey a tunneling behavior. That is, the PL quantum yield should increase exponentially with the shell thickness. The ligand FRET is an electromagnetic coupling between the quantum dot state and the vibrations on the surface. So as we grow this shell, we should expect the PL quantum yield to increase as a fourth power of the total nanoparticle radius. Since phonon relaxation is intrinsic to the core material, the growth of the shell should not have any effect, and we should expect the quantum yield to be independent of the shell thickness. So over here, we have an elegant method to determine the non-radiative mechanism. All we have to do is to grow a thick shell around the nanoparticle, measure the quantum yield as a function of shell thickness, and compare to these three models to determine the mechanism. Nobody has grown a thick shell around mid-infrared quantum dots before. So I first developed a synthesis strategy to grow the shell. We have used mercury selenide as the model system for mid-infrared transitions, and I have grown a thick cadmium sulfide shell around these mercury selenide core quantum dots. As we can see from these electron microscopy images, we are able to grow thick shells roughly uniformly up to thicknesses of 7 nanometers. So now that we have a method to grow a shell around the quantum dot, we need to look at the quantum yield as a function of thickness to determine the mechanism. Here I have the main results of my work. The black data points are measured quantum yields for core shell nanoparticles with different shell thicknesses. We can see immediately that growth of this thick shell leads to a dramatic increase in the quantum yield, and the non-radiative lifetime corresponds to 15 nanoseconds, which is 10 times larger than the previous record. For the thickest samples, the PL quantum yield is 2%. And this is the brightest quantum yield for any material in solution at this wavelength at room temperature. So this shows that these quantum dots are excellent materials for making efficient mid-infrared LEDs. By comparing the experimental trend with the three models, we can see that the experimental trend matches fairly well with the ligand FRET model. Though the agreement is not great and there is deviation for the larger thickness, this disagreement is likely due to the growth of the shell not being perfectly spherical, and there being defects at the core shell interface, which reduce the quantum yield. But overall, this result shows that ligand FRET is likely the dominant non-radiative mechanism. So to summarize my work, the main motivation for my project is to make sensitive mid-infrared cameras which have background limited detection near room temperature. And to do this, it is necessary to slow the non-radiative decay. To find the mechanism of non-radiative relaxation, I have designed a method to grow a thick shell around the quantum dots. So we were able to grow a thick cadmium sulfide shell around mercury selenide quantum dots. And by measuring the quantum yield as a function of thickness, we were able to see a dramatic increase in the non-radiative lifetime. To tie this result back to my original motivation, this work shows the importance of engineering the surface of the quantum dot to obtain a slow non-radiative decay. So this tells us that for us to get efficient mid-infrared detectors, it is necessary to overcome this ligand FRET relaxation, either by growing a shell or by modifying the ligands on the surface. I want to end my talk by discussing my plans for the future. The quantum yield of the quantum dots decreases as we increase the doping, and this is a major challenge for obtaining bright mid-infrared emission. We are attributing this to defects at the core shell interface due to the lattice mismatch between mercury selenide and Cat sulfide. We are looking for a method to characterize these defects at the interface. We're looking for a method to directly measure the absorption of the ligands on the surface of the quantum dots, so we can prove that ligand FRET is indeed the dominant mechanism. And we are planning to fabricate mid-infrared LEDs using these quantum dots. So if you have any ideas or you have expertise in instrumentation which can address these questions, please contact me and I would be happy to chat with you. I want to thank my advisor, Philippe, my collaborator, Chris, the group members of the PGS group, and I want to thank my funders, and I would be happy to answer any questions. Thank you.